many books, including the most recent book series called The Biggest Ideas in the Universe. The first book of which is titled Space, Time, and Motion, and it's on the topic of general relativity. And the second, coming out on May 14th, so you should definitely pre-order it, is titled Quanta and Fields, and that one is on the topic of quantum mechanics. Sean is a legit active theoretical physicist and at the same time is one of the greatest communicators of physics ever. I highly encourage you to listen to his podcast, read his books, and pre-order the new book to support his work. This was, as always, a big honor and a pleasure for me. This is the Lex Fridman Podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Sean Carroll. In book one of the series, The Biggest Ideas in the Universe, called Space, Time, Motion, you take on classical mechanics, general relativity, by taking on the main equation of general relativity and making it accessible, easy to understand. So maybe at the high level, what is general relativity? What's a good way to start to try to explain it?
Probably the best way to start to try to explain it is special relativity, which came first, 1905. It was the culmination, right, of many decades of people putting things together, but it was Einstein in 1905. In fact, it wasn't even Einstein. I should give more credit to Minkowski in 1907. So Einstein in 1905 figured out that you could get rid of the ether, the idea of a rest frame for the universe, and all the equations of physics would make sense, with the speed of light being a maximum. But then it was Minkowski, who used to be Einstein's professor.
In book one of the series, The Biggest Ideas in the Universe, called Space, Time, Motion, you take on classical mechanics, general relativity, by taking on the main equation of general relativity and making it accessible, easy to understand. So maybe at the high level, what is general relativity? What's a good way to start to try to explain it?
Probably the best way to start to try to explain it is special relativity, which came first, 1905. It was the culmination, right, of many decades of people putting things together, but it was Einstein in 1905. In fact, it wasn't even Einstein. I should give more credit to Minkowski in 1907. So Einstein in 1905 figured out that you could get rid of the ether, the idea of a rest frame for the universe, and all the equations of physics would make sense, with the speed of light being a maximum. But then it was Minkowski, who used to be Einstein's professor in 1907, who realized the most elegant way of thinking about this idea of Einstein's was to blend space and time together into space-time, to really imagine that there is no hard and fast division of the four-dimensional world in which we live to space and time separately. Einstein was at first dismissive of this. He thought it was just like, oh, the mathematicians are over-formalizing again. But then he later realized that if space-time is a thing, it can have properties. And in particular, it can have a geometry. It can be curved from place to place. And that was what let him solve the problem of gravity. He had previously been trying to fit in what we knew about gravity from Newtonian mechanics, the inverse square law of gravity, to his new relativistic theory. It didn't work. So the final leap was to say gravity is the curvature of space-time. And that statement is basically general relativity.
And the tension with Minkowski was, he was a mathematician.
Yes.
So there's a tension between physics and mathematics. In fact, in your lecture about this equation, one of them, you say that Einstein is a better physicist than he gets credit for.
I know, that's hard. That's a little bit of a joke there, right?
Yeah.
Because we all give Einstein a lot of credit, but then we also, partly based on fact, but partly to make ourselves feel better, tell ourselves a story about how later in life Einstein couldn't keep up. There were younger people doing quantum mechanics and quantum field theory and particle physics, and he was just sort of unable to really philosophically get over his objections to that. And I think that that story about the latter part is completely wrong, like almost 180 degrees wrong. I think that Einstein understood quantum mechanics as well as anyone, at least up through the 1930s. I think that his philosophical objections to it are correct, so he should actually have been taken much more seriously about that. And what he achieved in trying to think these problems through is to really basically understand the idea of quantum entanglement, which is kind of important these days when it comes to understanding quantum mechanics. Now, it's true that in the 40s and 50s, he placed his efforts in hopes for unifying electricity and magnetism with gravity that didn't really work out very well. All of us, try things that don't work out. I don't hold that against him. But in terms of IQ points, in terms of trying to be a clear-thinking physicist, he was really, really great.
What does greatness look like for a physicist? So how difficult is it to take the leap from special relativity to general relativity? How difficult is it to imagine that, to consider space-time together, and to imagine that there's a curvature to this whole thing?
Yeah, that's a great question. I think that if you want to make the case for Einstein's greatness, which is not hard to do, there's two things you point at. One is in 1905, his famous miracle year, he writes 3 different papers on 3 wildly different subjects, all of which would make you famous just for writing that one paper. Special relativity is one of them. Brownian motion is another one, which is just, little vibrations of tiny little dust specks in the air. But who cares about that? What matters is it proves the existence of atoms. He explains Brownian motion by imagining there are molecules in the air and deriving their properties. Brilliant. And then he basically starts the world on the road to quantum mechanics with his paper on, which again is given a boring label of the photoelectric effect. What it really was is he invented photons. He showed that light should be thought of as particles as well as waves. And he did all 3 of those very different things in 1 year. Okay. But the other thing that gets him genius status is, like you say, general relativity. So this takes 10 years, from 1905 to 1950. He wasn't only doing general relativity. He was working on other things. He invented a refrigerator. He did various interesting things. And he wasn't even the only one working on the problem. There were other people who suggested relativistic theories of gravity. But he really applied himself to it, and I think as your question suggests, the solution was not a matter of turning a crank. It was something fundamentally creative. In his own telling of the story, his greatest moment, his happiest moment, was when he realized that the way that we would say it in modern terms, if you were in a rocket ship, accelerating at 1g, at 1 acceleration due to gravity, if the rocket ship were very quiet, you wouldn't be able to know the difference between being in a rocket ship and being on the surface of the Earth. Gravity is sort of not detectable, or at least not distinguishable from acceleration. So number one, that's a pretty clever thing to think. But number two, if you or I had had that thought, we would have gone, we're pretty clever. He reasons from there to say, okay, if gravity is not detectable, then it can't be like an ordinary force, right? The electromagnetic force is detectable. You can put charged particles around. Positively charged particles and negatively charged particles respond differently to an electric field or to a magnetic field. He realizes that what his thought experiment showed, or at least suggested, is that gravity isn't like that. Everything responds in the same way to gravity. How could that be the case? And then this other leap he makes is, it's because it's the curvature of space-time, right? It's a feature of space-time. It's not a force on top of it. And the feature that it is curvature. And then finally, he says, okay, clearly I'm going to need the mathematical tools necessary to describe curvature. I don't know them, so I will learn them. And they didn't have MOOCs or AI helpers back in those days. He had to sit down and read the math papers, and he taught himself differential geometry and invented general relativity.
What about the step of including time as just another dimension? So combining space and time. Is that a simple mathematical leap, as Minkowski suggested?
It's certainly not simple, actually. It's a profound insight. That's why I said I think we should give Minkowski more credit than we do. He's the one who really put the finishing touches on special relativity. Again, many people had talked about how things change when you move close to the speed of light, what Maxwell's equations of electromagnetism predict and so forth, what their symmetries are. So people like Lorentz and Fitzgerald and Poincaré, there's a story that goes there. And in the usual telling, Einstein sort of puts the capstone on it. He's the one who says, All of this makes much more sense if there just is no ether. It is undetectable. We don't know how fast. Everything is relative, thus the name relativity. But he didn't take the actual final step, which was to realize that the underlying structure that he had invented is best thought of as unifying space and time together. I honestly don't know what was going through Minkowski's mind when he thought that. I'm not sure if he was, so mathematically adept that it was just clear to him, or he was really struggling it and he did trial and error for a while. I'm not sure.
I mean, do you, for him or for Einstein, visualize the four-dimensional space and try to play with the idea of time as just another dimension?
Oh yeah, all the time. I mean, we of course make our lives easy by ignoring two of the dimensions of space. So instead of four-dimensional space-time, we just draw pictures of one dimension of space, one dimension of time, the so-called space-time diagram. But, maybe this is lurking underneath your question, but even the best physicists will draw, a vertical axis and a horizontal axis. And we'll go space, time. But deep down, that's wrong, because you're sort of preferring one direction of space and one direction of time, and it's really the whole two-dimensional thing that is space-time. The more legitimate thing to draw on that picture are rays of light, are light cones. From every point, there is a fixed direction at which the speed of light would represent, and that is actually inherent in the structure. The division into space and time is something that's easy for us human beings.
What is the difference between space and time from the perspective of general relativity?
It's the difference between x and y when you draw axes on a piece of paper.
So there's really no difference?
There's almost no difference. There's one difference that is kind of important, which is the following. If you have a curve in space, I'm going to draw it horizontally because that's usually what we do in space-time diagrams. If you have a curve in space, you've heard the motto before that the shortest distance between 2 points is a straight line. If you have a curve in time, which is, by the way, literally all of our lives, right? We all evolve in time. So you can start with one event in space-time and another event in space-time. What Minkowski points out is that the time you measure along your trajectory in the universe is precisely analogous to the distance you travel on a curve through space. And by precisely, I mean it is also true that the actual distance you travel through depends on your path, right? Go a straight line, shortest distance, and curvy line to be longer. The time you measure in space-time, the literal time that ticks off on your clock, also depends on your path. But it depends on it the other way. So that the longest time between 2 points is a straight line. And if you zig back and forth in space-time, you take less and less time to go from point A to point B.
How do we make sense of that? The difference between the observed reality and the objective reality underneath it? Or is objective reality a silly notion, given general relativity?
I'm a huge believer in objective reality. I think that objective reality,
You're a fan.
is real.
Yeah.
But I do think that people kind of are a little overly casual about the relationship between what we observe and objective reality in the following sense. Of course, in order to explain the world, our starting point and our ending point is our observations, our experimental input, the phenomena we experience and see around us in the world. But in between, there's a theory. There's a mathematical formalization of our ideas about what is going on. And if a theory fits the data and is very simple and makes sense in its own terms, then we say that the theory is right. And that means that we should attribute some reality to the entities that play an important role in that theory, at least provisionally until we come up with a better theory down the road.
I think a nice way to test the difference between objective reality and observed reality is what happens at the edge of the horizon of a black hole. So technically, as you get closer to that horizon, time stands still.
Yes and no. It depends on exactly how careful we're being. So here is a bunch of things I think are correct. If you imagine there is a black hole space-time, so like the whole solution to Einstein's equation, and you treat you and me as what we call test particles. So we don't have any gravitational fields ourselves. We just move around in the gravitational field. And that's obviously an approximation, okay? But let's imagine that. And you stand outside the black hole, and I fall in. And as I'm falling in, I'm waving to you, because I'm going into the black hole, you will see me move more and more slowly. And also the light from me is redshifted, so I'm a little embarrassed because I'm falling into a black hole. And there is a limit. There's a last moment that light will be emitted from me, from your perspective, forever, okay? Now you don't literally see it because I'm emitting photons more and more slowly, right? Because from your point of view. So it's not like I'm equally bright. I basically fade from view in that picture, okay? So that's one approximation. The other approximation is I do have a gravitational field of my own, and therefore as I approach the black hole doesn't just sit there and let me pass through, it kind of moves out to eat me up, because its net energy mass is going to be mine plus its. But roughly speaking, yes, I think so. I don't like to go to the dramatic extremes because that's where the approximations break down. But if you see something falling into a black hole, you see its clock ticking more and more slowly.
How do we know it fell in?
We don't. I mean, how would we? Because it's always possible that right at the last minute it had a change of heart and starts accelerating away, right? If you don't see it pass in, you don't know. And let's point out that as smart as Einstein was, he never figured out black holes, and he could have. It's kind of embarrassing. It took decades for people thinking about general relativity to understand that there are such things as black holes, because basically Einstein comes up with general relativity in 1915. 2 years later, Carl Schwarzschild, derives the solution to Einstein's equation that represents a black hole, the Schwarzschild solution. No one recognized it for what it was until the 50s, David Finkelstein and other people. And that's just, one of these examples of physicists not being as clever as they should have been.
Well, that's the singularity. That's the kind of the edge of the theory, the limit. So it's understandable that it's difficult to imagine the limit of things.
It is absolutely hard to imagine, and a black hole is very different in many ways from what we're used to. On the other hand, I mean, the real reason, of course, is that between 1915 and 1955, there's a bunch of other things that are really interesting going on in physics, all of particle physics and quantum field theory. So many of the greatest minds were focused on that. But still, if the universe hands you a solution to general relativity in terms of curved space-time, and it's kind of mysterious, certain features of it, I would put some effort into trying to figure it out.
So how does a black hole work? Put yourself in the shoes of Einstein and take general relativity to its natural conclusion about these massive things.
It's best to think of a black hole as not an object so much as a region of space-time, okay? It's a region with the property, at least in classical general relativity. Quantum mechanics makes everything harder, but let's imagine we're being classical for the moment. It's a region of space-time with the property that if you enter, you can't leave. Literally, the equivalent of escaping a black hole would be moving faster than the speed of light. They're both precisely equally difficult. You would have to move faster than the speed of light to escape from the black hole. So once you're in, that's fine. In principle, you don't even notice when you cross the event horizon, as we call it. The event horizon is that point of no return, where once you're inside, you can't leave. But meanwhile, the space-time is sort of collapsing around you to ultimately a singularity in your future, which means that the gravitational forces are so strong they tear your body apart, and you will die in a finite amount of time. The time it takes, if the black hole is about the mass of the sun, to go from the event horizon to the singularity takes about 1/1,000,000th of a second.
And what happens to you if you fall into the black hole? Like, if we think of an object as information, that information gets destroyed.
Well, you've raised a crucially difficult point. So that's why I keep needing to distinguish between black holes according to Einstein's theory of general relativity, which is book 1 of Space-Time and Geometry, which is perfectly classical. And then come the 1970s, we start asking about quantum mechanics and what happens in quantum mechanics. According to classical general relativity, the information that makes up you when you fall into the black hole is lost to the outside world. It's there, it's inside the black hole, but we can't get it anymore. in the 1970s, Stephen Hawking comes along and points out that black holes radiate. They give off photons and other particles to the universe around them, and as they radiate, they lose mass, and eventually they evaporate, they disappear. So once that happens, I can no longer say the information about you or a book that I threw in the black hole or whatever is still there, is hidden behind the black hole, because the black hole has gone away. So either that information is destroyed, like you said, or it is somehow transferred to the radiation that is coming out, to the Hawking radiation. The large majority of people who think about this believe that the information is somehow transferred to the radiation and information is conserved. That is a feature both of general relativity by itself and of quantum mechanics by itself. So if you put them together, that should still be a feature. We don't know that for sure. There are people who have doubted it, including Stephen Hawking for a long time. But that's what most people think. And so what we're trying to do now in a topic which has generated many, many hundreds of papers called the Black Hole Information Loss Puzzle is figure out how to get the information from you or the book into the radiation that is escaping the black hole.
Is there any way to observe Hawking radiation to a degree where you can start getting insight? Or is this all just in the space of theory right now?
Right now, we are nowhere close to observing Hawking radiation. Here's the sad fact. The larger the black hole is, the lower its temperature is. So, a small black hole, like a microscopically small black hole, might be very visible. It's giving off light. But something like the black hole at the center of our galaxy, 3 million times the mass of the sun or something like that, Sagittarius A star, that is so cold and low temperature that its radiation will never be observable. Black holes are hard to make. We don't have any nearby. The ones we have out there in the universe are very, very faint. So there's no immediate hope for detecting Hawking radiation.
Allegedly, we don't have any nearby.
As far as we know, we don't have any nearby.
Could tiny ones be hard to detect somewhere
Absolutely.
at the edges of the solar system? Maybe?
So you don't want them to be too tiny or they're exploding, right? Or they're very bright and then they would be visible. But there's absolutely a regime where black holes are large enough not to be visible because the larger ones are fainter, right? Not giving off radiation, but small enough to not been detected through their gravitational effect. Yeah.
Psychologically, just emotionally, how do you feel about black holes? They scare you?
I love them. I love black holes. But the universe weirdly makes it hard to make a black hole. Right? Because you really need to squeeze an enormous amount of matter and energy into a very, very small region of space. So we know how to make stellar black holes. A supermassive star can collapse to make a black hole. We know we also have these supermassive black holes, the center of galaxies. We're a little unclear where they came from. I mean, maybe stellar black holes that got together and combined, but that's, one of the exciting things about new data from the James Webb Space Telescope is that quite large black holes seem to exist relatively early in the history of the universe. So it was already difficult to figure out where they came from. Now it's an even tougher puzzle.
So these supermassive black holes are formed somewhere early on in the universe. I mean, that's a feature, not a bug, right? That we don't have too many of them. Otherwise, we wouldn't have the time or the space to form the little pockets of complexity that we call humans.
I think that's fair, yeah. It's always interesting when something is difficult but happens anyway, right? I mean, the probability of making a black hole could have been 0. It could have been 1. But it's this interesting number.
Moly, you kidding me right now?
Are there more intelligent alien civilizations than there are supermassive black holes?
Yeah,
what?
I have
What do you
no
mean, what?
idea.
Hallucinations,
But I think
like the ones from
your intuition is right
1961.
that
It happened again, just a
it
quick
would have been
blip, like
easy
blinking your-
for
Wait,
there to be lots of
didn't see it?
civilizations, and then we would have
I
noticed
was in
them
a
all.
total blackout.
And
Colossal
we
Cappy
haven't.
fried
So
my systems.
absolutely the simplest
Right, because
explanation
the
for
driver
why we
had
haven't
first
is that
aid
they're not
Cappy
big.
didn't work out like you
Yeah.
said. What? Big
I just
surprise.
think it's so
Betty
easy to make
Francis,
them.
the driver's
So there
alive
must
and
be-
your
I
remnants
understand that's the
verified.
simplest
Isn't that all you wanted?
But
Now,
also,
How easy
why
is
are
it to
you
make
two
life?
yapping about the
Eukaryotic life or
hallucination?
multicellular life?
When
it
Cappy
seems like
amplified the
life
remnant
finds a
signal,
way.
it triggered
Intelligent alien
another hallucination
civilization, sure,
event.
maybe
but
there
it
is
only lasted 3
somewhere
seconds
along that
this time.
chain
And
that
not only
really,
that,
really
we
hardly.
picked up that its source
But
was
once
northwest
you
of us,
start life,
specifically.
once you get the origin of life,
somewhere in the
it
deep
seems
zone.
like life just finds a way everywhere, in every
It's
condition.
been
They just figure it
40
out.
years.
I mean, I get it. I get exactly what you're thinking. I think it's a perfectly reasonable attitude to have before you confront the data. I would not have expected Earth to be special in any way. I would have expected there to be plenty of very noticeable extraterrestrial civilizations out there. But even if life finds a way, even if we buy everything you say, how long does it take for life to find it? What if it typically takes 100 billion years? Then we'd be alone.
So it's a time thing. So do you really, most likely there's no alien civilization out there?
And it turns out
I can't see it. I believe there's a ton of them, and there's another explanation why we can't see them.
I don't believe that very strongly. Look, I'm not going to place a lot of bets here. I would not. I'm both pretty up in the air about whether or not life itself is all over the place. It's possible when we visit other worlds, other solar systems, there's very tiny microscopic life ubiquitous, but none of it has reached some complex. It's also possible there isn't any. It's also possible that there are intelligent civilizations that have better things to do than knock on our doors. So I think we should be very humble about this.
And it's also possible there's a great filter where there's something fundamental about once a civilization develops complex enough technology, that technology is more statistically likely to destroy everybody versus to continue being creative.
That is absolutely possible. I'm actually putting less credence on that one just because you need it to happen every single time, right? If even one, I mean, this goes back to von Neumann. John von Neumann pointed out that you don't need to send the aliens around the galaxy. You can build self-reproducing probes and send them around the galaxy. And you might think, well, the galaxy is very big. It's really not. It's some tens of thousands of light years across and billions of years old. So you don't need to move at a high fraction of the speed of light to fill the galaxy.
So if you were an intelligent alien civilization, the dictator of one, you would just send out a lot of probes, self-replicating.
100%. And
spread out.
Yes. And what you should do, so if you want the optimistic spin, here's the optimistic spin. People looking for intelligent life elsewhere often tune in with their radio telescopes, right? At least we did before Arecibo was decommissioned. That's not a very promising way to find intelligent life elsewhere, because why in the world would a super intelligent alien civilization waste all of its energy by beaming it in random directions into the sky? For one thing, it just passes you by, right? So if we're here on Earth, we've only been listening to radio waves for a couple hundred years, okay? So if an intelligent alien civilization exists for a billion years, they have to pinpoint exactly the right time to send us this signal. It is much, much more efficient to send probes and to park, to go to the other solar systems, just sit there and wait for an intelligent civilization to arise in that solar system. This is kind of the 2001 monolith hypothesis, right? I would be less surprised to find a sort of quiescent alien artifact in our solar system than I would to catch a radio signal from an intelligent civilization.
So you're a sucker for in-person conversations versus remote.
I just want to integrate over time.
Mm-hmm.
A probe can just sit there and wait, whereas a radio wave goes right by you.
How hard is it for an alien civilization, again, you're the dictator of one, to figure out a probe that is most likely to find a common language with whatever it finds?
Couldn't that be like the elected leader of the alien
democratic leader, elected leader of a democratic alien civilization, yes.
I think we would figure out that language thing pretty quickly. I mean, maybe not as quickly as we do when different human tribes find each other, because obviously there's a lot of commonalities in humanity, but there is logic in math, and there is the physical world. You can point to a rock and go, rock, right? I don't think it would take that long. I know that Arrival, the movie, based on a Ted Chiang story, suggested that the way that aliens communicate is going to be fundamentally different, but also they had recognition and other things I don't believe in. So I think that if we actually find aliens, that will not be our long-term problem.
So there's a folks, one of the places you're affiliated with is Santa Fe, and they approach the question of complexity in many different ways and ask the question in many different ways of what is life, and thinking broadly. So to you, we'll be able to find it. You'll think you show up, probe shows up to a planet, we'll see a thing and be like, yeah, that's a living thing.
Well, again, if it's intelligent and technologically advanced, the more short-term question of if we get some spectroscopic data from an exoplanet, so we know a little bit about what is in its atmosphere, how can we judge whether or not that atmosphere is giving us a signature of life existing? That's a very hard question. People are debating it. I mean, one very simple-minded but perhaps interesting approach is to say small molecules don't tell you anything, because even if life could make them, something else could also make them. But long molecules, that's the kind of thing that life knows.
Size and complexity. I don't know. I just have this nervous feeling that we won't be able to detect. We'll show up to a planet, have a bunch of liquid on it. We take a swim in the liquid, and we won't be able to see the intelligence in it. Whether that intelligence looks like something like, ants, or we'll see movement, perhaps, strange movement, but we won't be able to see the intelligence in it or communicate with it. I guess if we have nearly infinite amount of time to play with different ideas, we might be able to.
I'm in favor of this kind of humility, this intellectual humility that we won't know, because we should be prepared for surprises. But I do always keep coming back to the idea that we all live in the same physical universe. And let's put it this way. The development of our intelligence has certainly been connected to our ability to manipulate the physical world around us. And so I would guess, without 100% credence by any means, but my guess would be that any advanced kind of life would also have that capability. Both dolphins and octopuses are potential counterexamples to that, but I think in the details there would be enough similarities that we would recognize.
I don't know how we got on this topic, but I think it was from supermassive black holes. So if we return to black holes and talk about the holographic principle more broadly, you have a recent paper on the topic. Been thinking about the topic in terms of rigorous research perspective and just as a popular book writer. So what is the holographic principle?
Well, it goes back to this question that we were talking about with the information and how it gets out. In quantum mechanics, certainly, arguably even before quantum mechanics comes along in classical statistical mechanics, there's a relationship between information and entropy. Entropy is my favorite thing to talk about. I've written books about, will continue to write books about. So Hawking tells us that black holes have entropy. And it's a finite amount of entropy. It's not an infinite amount. But the belief is, and now we're already getting quite speculative, the belief is that the entropy of a black hole is the largest amount of entropy that you can have in a region of space-time. It's sort of the most densely packed that entropy can be. And what that means is there's sort of a maximum amount of information that you can fit into that region of space, and you call it a black hole. And interestingly, you might expect if I have a box that I'm going to put information in it, and I don't tell you how I'm going to put the information in, but I ask, how does the information I can put in scale with the size of the box? You might think, well, it goes as the volume of the box, because the information takes up some volume, and I can only fit in a certain amount. And that is what you might guess for the black hole, but it's not what the answer is. The answer is that the maximum information, as reflected in these black hole entropy, scales as the area of the black hole's event horizon, not the volume itself. So, people thought about that in both deep and superficial ways for a long time, and they proposed what we now call the holographic principle. That the way that space-time and quantum gravity convey information or hold information is not different bits or qubits for quantum information at every point in space-time. It is something holographic, which means it's sort of embedded in or located in, can be thought of as pertaining to one dimension less of the three dimensions of space that we live in. So in the case of the black hole, the event horizon is two-dimensional. in a three-dimensional universe. And the holographic principle would say all of the information contained in the black hole can be thought of as living on the event horizon rather than in the interior of the black hole. I need to say one more thing about that, which is that this was an idea. What the idea I just told you was the original holographic principle put forward by people like Gerard de Tooft and Leonard Susskind, the super famous physicist. Leonard Susskind was on my podcast and gave a great talk. He's very, very good at explaining these things.
Mindscape podcast.
Mindscape
Everybody should
podcast.
listen.
That's right. Yes.
And you don't just have physicists on.
I don't.
I love Mindscape.
Oh, thank you very much.
Curiosity driven.
Yeah, ideas.
Exploration of ideas.
from smart people, yeah. But anyway, what I was trying to get at with Susskind and also with Tooft were a little vague. They were a little hand-wavy about holography and what it meant. Where holography, the idea that information is sort of encoded on a boundary, really came into its own was with Juan Maldacena in the 1990s and the ADS CFD correspondence, which we don't have to get into any detail, but it's a whole full-blown theory. It's two different theories. One theory in n dimensions of space-time without gravity, and another theory in n+1 dimensions of space-time with gravity. And the idea is that this n-dimensional theory is, casting a hologram into the n+1 dimensional universe to make it look like it has gravity. And that's holography with a vengeance. And that's an enormous source of interest for theoretical physicists these days.
How should we picture what impact that has? The fact that you could store all the information you could think of as all the information that goes into a black hole can be stored at the event horizon.
Yeah, I mean, it's a good question. One of the things that quantum field theory indirectly suggests is that there's not that much information in you and me compared to the volume of space-time we take up. As far as quantum field theory is concerned, you and I are mostly empty space. And so we are not information dense, right? The density of information in us, or in a book, or a CD, or whatever, computer RAM, is indeed encoded by volume. Like there's different bits located at different points in space, but that density of information is super duper low. So we're just like the speed of light, or just like the Big Bang. For the information in a black hole, we are far away in our everyday experience from the regime where these questions become relevant. So it's very far away from our intuition. We don't really know how to think about these things. We can do the math, we don't feel it in our bones.
So you can just write off that weird stuff happens.
Well,
in a black
we'd like
hole.
to do better, but we're trying. I mean, that's why we have an information loss puzzle, because we haven't completely solved it. So here's just one thing to keep in mind. Once space-time becomes flexible, which it does according to general relativity, and you have quantum mechanics, which has fluctuations in virtual particles and things like that, the very idea of a location in space-time becomes a little bit fuzzy, right? Because it's flexible, and quantum mechanics says you can't even pin it down. So information can propagate in ways that we might not have expected. And that's easy to say, and it's true, but we haven't yet come up with the right way to talk about it that is perfectly rigorous.
It's crazy how dense of the information a black hole is, and then plus like quantum mechanics starts to come into play. So you almost want to romanticize the kind of interesting computation type things that are going on inside the black hole.
You do. But I'll point out one other thing. It's information dense, but it's also very, very high entropy. So a black hole is kind of like a very, very, very specific random number, right? It takes a lot of digits to specify it, but the digits don't tell you anything. They don't give you anything useful to work on. So it takes a lot of information, but it's not of a form that we can learn a lot from.
But hypothetically, I guess as you mentioned, the information might be preserved. The information that goes into a black hole doesn't get destroyed. So what does that mean when the entropy is really high?
Well, the black hole, I said that the black hole is the highest density of information, but it's not the highest amount of information, because the black hole can evaporate. And when it evaporates, and people have done the equations for this, when it evaporates, the entropy that it turns into is actually higher than the entropy of the black hole was, which is good because entropy is supposed to go up. But it's much more dilute, right? It's spread across a huge volume of space-time. So in principle, all that you made the black hole out of, the information that it took, is still there, we think, in that information, but it's scattered to the four.
We just talked about the event horizon of a black hole. What's on the inside? What's at the center of it?
No one's been there, so
Came back to
yeah,
tell.
this is a theoretical prediction. But I'll say one super crucial feature of the black holes that we know and love, the kind that Schwarzschild first invented. There's a singularity, but it's not at the middle of the black hole. Remember, space and time are parts of parts of one unified space-time. The location of the singularity in the black hole is not the middle of space, but our future. It is a moment of time. It is like a big crunch. The Big Bang was an expansion from singularity in the past. Big crunch probably doesn't exist, but if it did, it would be a collapse to a singularity in the future. That's what the interiors of black holes are like. You can be fine in the interior, but things are becoming more and more crowded. Space-time is becoming more and more warped, and eventually you hit a limit, and that's the singularity in your future.
I wonder what time is like on the inside of a black hole.
Time always ticks by at 1 second per second. That's all it can ever do.
Yeah.
Time can tick by differently for different people, and so you have things like the twin paradox, where two people initially are the same age, one goes off and the speed of light and comes back. Now they're not. It can even work out that the one who goes out and comes back will be younger because they did not take the shortest distance back. But locally, as far as you and your wristwatch are concerned, time is not fun. Time, your neurological signals in your brain and your heartbeat and your wristwatch, whatever's happening to them, is happening to all of them at the same time. So time always seems to be ticking along at the same time.
Well, if you fall into a black hole, and then I'm an observer just watching it, and then you come out once it evaporates 1 million years later, I guess you'd be exactly the same age? Have you aged at all?
You would be converted into photons.
Right. So it's not at all possible that the information is preserved exactly as it would.
It depends on the microscope. It's there in the microscopic configuration of a human. It's exactly as if I took a regular book, made of paper, and I burned it. The laws of physics say that all the information in the book is still there in the heat and light and ashes. We're never going to get it. It's a matter of practice, but in principle it's still there.
But what about the age of things from the observer perspective, from outside the black hole?
Outside the black hole, it doesn't matter because they're inside the black hole.
No, so but is there okay? There's no way to escape the black hole except
To let it happen.
letting it evaporate.
But also, by the way, just in relativity, special relativity, forget about general relativity, it's enormously tempting to say, okay, here's what's happening to me right now. I want to know what's happening far away right now. The whole point of relativity is to say there's no such thing as right now when you're far away. And that is doubly true for what's inside a black hole. So you're tempted to say, well, how fast is their clock ticking? Or how old are they now? Not allowed to say that for you.
Because space and time are treated the same, so it doesn't make sense. But what happens to time in the holographic prism?
As far as we know, nothing dramatic happened. We're not anywhere close to being confident that we know what's going on here yet. So there are good unanswered questions about whether time is fundamental, whether time is emergent, whether it has something to do with quantum entanglement, whether time really exists at all. Different theories, different proponents of different things. But there's nothing specifically about holography that would make us change our opinions about whatever they have to be.
But holography is fundamentally about it's a question of space.
It really is, yeah.
Okay, so time is just like a
Time just goes along, as far as we know. Yeah.
So all the questions about time is just almost like separate questions, whether it's emergent and all that.
Yeah,
kind of
I mean, that might be a reflection of our ignorance right now, but yes.
If we figure out a lot, millions of years from now about black holes, how surprised would you be if they travel back in time and told you everything you want to know about black holes? How much do you think there is still to know? And how mind-blowing would it be?
It does depend on what they would say. I think that there are colleagues of mine who think that we're pretty close figuring out how information gets out of black holes, how to quantize gravity, things like that. I'm more skeptical that we are pretty close. I think that there's room for a bunch of surprises to come. So in that sense, I suspect I would be surprised. The biggest and most interesting surprise to me would be if quantum mechanics itself were somehow superseded by something better. As far as I know, there's no empirical evidence-based reason to think that quantum mechanics is not 100% correct. But it might not be. That's always possible. So, and there are, again, respectable friends of mine who speculate about it. So that's something that's the first thing I would want to know.
Oh, so like the black hole would be the most clear illustration.
Yeah, that's where it would
If
show.
there's something you would show up there.
I mean, maybe. The point is that black holes are mysterious for various reasons. So, yeah, if our best theory of the universe is wrong, that might help explain why.
Do you think it's possible we'll find something interesting like black holes sometimes create new universes, or black holes are a kind of portal through space-time to another place? And then our whole conception of what is the fabric of space-time changes completely, because black holes, it's like Swiss cheese type of situation.
Yeah, that would be less surprising to me because I've already written papers about that. We don't have, again, strong reason to think that the interior of a black hole leads to another universe. But it is possible, and it's also very possible that that's true for some black holes and not others. This is stuff we don't know. It's easy to ask questions, we don't know the answer. The problem is, the questions that are easy to ask that we don't know the answer to are super hard to answer.
Because these objects are very difficult to test and to explore.
The regimes are just very far. So either literally far away in space, but also in energy or mass or time or whatever.
You've published a paper on the holographic principle, or that involves the holographic principle. What can you explain the details of that?
Yeah, I'm always interested in, since my first published paper, taking these wild speculative ideas and trying to test them against data. And the problem is, when you're dealing with wild speculative ideas, they're usually not well defined enough to make a prediction, right? Like, it's kind of, I know what's going to happen in some cases, I don't know what's going to happen in other cases. So we did the following thing. As I've already mentioned, the holographic principle, which is meant to reflect the information contained in black holes, seems to be telling us that there's less information, less stuff that can go on than you might naively expect. So let's upgrade naively expect to predict using quantum field theory. Quantum field theory is our best theory of fundamental physics right now. Unlike this holographic black hole stuff, quantum field theory is entirely local. In every point of space, something can go on, and then you add up all the different points in space. Okay, not holographic at all. So there's a mismatch between the expectation for what is happening, even in empty space, in quantum field theory, versus what the holographic principle would predict. How do you reconcile these two things? So there's one way of doing it that had been suggested previously, which is to say that in the quantum field theory way of talking, it implies there's a whole bunch more states, a whole bunch more ways the system could be than there really are. And just I'll do a little bit of math, just because there might be some people in the audience who like the math. If I draw two axes on a two-dimensional geometry, like the surface of the table, right? You know that the whole point of it being two-dimensional is I can draw two vectors that are perpendicular to each other. I can't draw three vectors that are all perpendicular to each other, right? They need to overlap a little bit. That's true for any numbers of dimensions. But I can ask, okay, how much do they have to overlap? If I try to put more vectors into a vector space than the dimensionality of the vector space, then I make them almost perpendicular to each other. And the mathematical answer is, as the number of dimensions gets very, very large, you can fit a huge extra number of vectors in that are almost perpendicular to each other. So, in this case, what we're suggesting is the number of things that can happen in a region of space is correctly described by holography. It is somewhat overcounted by quantum field theory, but that's because the quantum field theory states are not exactly perpendicular to each other. I should have mentioned that in quantum mechanics, states are given by vectors in some huge dimensional vector space. Very, 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 very large dimensional vector space. So maybe the quantum field theory states are not quite perpendicular to each other. If that is true, that's a speculation already, but if that's true, how would you know? What is the experimental deviation? And it would have been completely respectable if we'd gone through, made some guesses, and found that there is no noticeable experimental difference because, again, these things are in regimes very, very far away. We stuck our necks out. We made some very, very specific guesses as to how this weird overlap of states would show up in the equations of motion for particles like neutrinos. And then we made predictions on how the neutrinos would behave on the basis of those wild guesses. And then we compared them with data. And what we found is we're pretty close, but haven't yet reached the detectability of the effect that we are predicting. In other words, well, basically one way of saying what we predict is if a neutrino, and there's reasons why it's neutrinos, we can go into if you want, but it's not that interesting. A neutrino comes to us from across the universe, from some galaxy very, very far away. There is a probability as it's traveling that it will dissolve into other neutrinos because they're not really perpendicular to each other as vectors as they would ordinarily be in quantum field theory. And that means that if you look at neutrinos coming from far enough away with high enough energies, they should disappear. Like if you see a whole bunch of nearby neutrinos, but then further away, you should see fewer. And there's an experiment called IceCube, which is this amazing testament to the ingenuity of human beings, where they go to Antarctica and they drill holes and they put photodetectors on a string a mile deep in these holes, and they basically use all of the ice in a cube. I don't know whether it's a mile or not, but it's like a kilometer or something like that, some big region. That much ice is their detector. And they're looking for flashes when a cosmic ray or a neutrino or whatever hits ice molecule, water molecule in the ice.
Flashes in the ice.
Yes, they're looking for flashes in the ice.
Isn't there some crazy, what does the detector of that look like?
It's a bunch of strings, many, many, many strings with 360-degree photodetectors.
Yeah.
And you will...
That's really cool.
It's extremely cool.
Yeah.
They've done amazing work, and they find neutrinos.
So they're looking for neutrinos.
Yeah, so the whole point is most cosmic rays are protons. Because why? Because protons exist, and they're massive enough that you can accelerate them to very high energies. So high energy cosmic rays tend to be protons. They also tend to hit the Earth's atmosphere and decay into other particles. So neutrinos, on the other hand, punch right through, at least usually, right, to a great extent. So not just Antarctica, but the whole Earth. Occasionally, a neutrino will interact with a particle here on Earth. There's neutrinos going through your body all the time, from the sun, from the universe, etc. And so if you're patient enough and you have a big enough part of the Antarctic ice sheet to look at, the nice thing about ice is it's transparent. So you've built yourself, nature has built you a neutrino detector.
So why
IceCube does.
Why ice? So is it just because of the low noise and you get to watch this thing and it's
much more dense than air, but it's transparent.
So you have much more dense, so high probability, and then it's transparency, and then it's also in the middle of nowhere, so
Well, that's all you need. There's not that much ice, right? Yeah. So
Humans
there's more
are
ice in
best.
Antarctica than anywhere else, right? So anyway, you can go and you can get a plot from the IceCube experiment. How many neutrinos there are that they detected with very high energies. And we predict in our weird little holographic guessing game that there should be a cutoff. You should see neutrinos as you get to higher and higher energies, and then they should disappear. If you look at the data, their data gives out exactly where our cutoff is. That doesn't mean that our cutoff is right. It means they lose the ability to do the experiment exactly where we predict the cutoff should be.
Oh boy. Okay. But why is there a limit?
Oh, just because there are fewer high energy neutrinos. So there's a spectrum, and it goes down. But what we're plotting here is number of neutrinos versus energy. It's fading away, and they just get very, very few.
And you need the high energy neutrinos for your
Our
prediction.
effect is a little bit bigger for high energies. Yeah.
Got it. And that effect has to do with this almost perpendicular thing.
And let me just mention the name of Oliver Friedrich, who was a postdoc who led this. He deserves the credit for doing this. I was a co-author and a collaborator. I did some work, but he really gets the credit.
Thank you, Oliver. Thank you for pushing this wild-sized forward. Just to speak to that, the meta process of it, how do you approach asking these big questions and trying to formulate it as a paper, as an experiment, and make a prediction, all that kind of stuff? What's your process?
There's a very interesting things that happens once you're a theoretical physicist, once you become trained, graduate student, written some papers and whatever. Suddenly you are the world's expert in a really infinitesimally tiny area of knowledge, right? And you know not that much about other things. There's an overwhelming temptation to just drill deep, right? Just keep doing basically the thing that you started doing. But maybe that thing you started doing is not the most interesting thing to the world or to you or whatever. So you need to separately develop the capability of stepping back and going, okay,
I owe you an
now
apology.
that I can write papers in
I
that
screwed
area,
up. I nearly got you
now that I'm
killed.
sort of trained enough in the
things I
general
used to calculate as
procedure,
easily as turning a screwdriver.
what is the
foggy
best
now.
match
The numbers
between
don't
my
work themselves
interests,
out like they used
my
to.
abilities,
I haven't
and
been
what is
myself
actually
for a long
interesting?
time.
And
But I haven't
honestly,
needed to be.
I've not
It's
been very
me
good at
and
that
this cursed
over
place
my
I created
career.
and nothing else for decades.
You know, I have
knowing that
my
whatever caused the mass
process
hallucination is
traditionally
still out
was I
there.
was working in this
I need
general
to know what it
area
is,
of
and why the remnants are
particle
connected to
physics,
it.
field theory, general
Francis
relativity,
was right about
cosmology,
the remnant and the mass
and I
hallucinations
would
paired
sort
signals.
of
If we can get them together, maybe
try to
they'll
take
cancel each
things
other
other
out,
people were
we'll be
talking
free.
about
It's a
and
shaky
ask
theory
myself
at
whether or
best, but
not
it's the
it
only
really
lead we've
fit
got for
together.
now.
Like
You can do
my
nothing and
my
twiddle your
two,
thumbs
so
until
I guess
the
I have
remnant
3
drives you
papers
mad.
that I've ever written
Or, if you're willing to
that
work with
have
me,
done
I'll
super
give
well
you the
in terms of
best
getting
chance to
cited and
survive
things
this
like that.
thing.
One
Think
was my
it
first
through.
ever paper that I get
fix
very
up
little
your
credit
car while you're
for.
doing
That
it.
was my
You'll need
advisor
to
and
for
his
whatever you decide
collaborator,
from
you know,
here.
set that up. The other 2 were basically my idea. One was right after we discovered that the universe was accelerating. So in 1998, observations showed that not only is the universe expanding, but it's expanding faster and faster. So that's attributed to either Einstein's cosmological constant or some more complicated form of dark energy, some mysterious thing that fills the universe. And people were throwing around ideas about this dark energy stuff, what could it be, and so forth. Most of the people throwing around these ideas were cosmologists. They work on cosmology. They think about the universe all at once. Since I like to talk to people in different areas, I was sort of more familiar than average with what a respectable working particle physicist would think about these things. And what I immediately thought was, you guys are throwing around these theories. These theories are wildly unnatural. They're super finely tuned. Like any particle physicist would just be embarrassed to be talking about this. But rather than just scoffing at them, I sat down and asked myself, okay, is there a respectable version? Is there a way to keep the particle physicist happy but also make the universe accelerate? And I realized that there is some very specific set of models that is relatively natural, and guess what? You can make a new experimental prediction on the basis of those. And so I did that. People were very happy about that.
What was the thing that would make physicists happy, that would make sense of this fragile thing that people call dark energy?
So the fact that dark energy pervades the whole universe and is slowly changing, that should immediately set off alarm bells, because particle physics is a story of length scales and time scales that are generally, guess what? Small, right? Particles are small, they vibrate quickly, and you're telling me now I have a new field and its typical rate of change is once every billion years, right? Like that's just not natural. And indeed, you could formalize that and say, look, even if you wrote down a particle that evolved slowly over billions of years, if you let it interact with other particles at all, that would make it move faster. Its dynamics would be faster. Its mass would be higher, et cetera, et cetera. So there's a whole story. Things need to be robust, and they all talk to each other in quantum field theory. So how do you stop that from happening? And the answer is symmetry. You can impose a symmetry that protects your new field from talking to any other fields, okay? And this is good for 2 reasons. Number one, it can keep the dynamics slow. So if you can't tell me why it's slow, you just made that up, but at least it can protect it from speeding up because it's not talking to any other particles. And the other is it makes it harder to detect. naively, experiments looking for fifth forces or time changes of fundamental constants of nature like the charge of the electron, these experiments should have been able to detect these dark energy fields. And I was able to propose a way to stop that from happening.
The detection.
The detection, yeah. Because a symmetry could stop it from interacting with all these other fields, and therefore makes it harder to detect. And just by luck, I realized, because it was actually based on my first ever paper, there's one loophole. If you impose these symmetries, so you protect the dark energy field from interacting with any other fields, there's one interaction that is still allowed, that you can't rule out. And it is a very specific interaction between your dark energy field and photons, which are very common. And it has the following effect. As a photon travels through the dark energy, the photon has a polarization, up, down, left, right, whatever it happens to be. And as it travels through the dark energy, that photon will rotate its polarization. This is called birefringence. And you can kind of run the numbers and say, you can't make a very precise prediction, so you're just making up this model, but if you want to roughly fit the data, you can predict how much polarization rotation there should be. A couple of degrees, okay? Not that much. So that's very hard to detect. People have been trying to do it. Right now, literally, we're on the edge of either being able to detect it or rule it out using the cosmic microwave background. And there is just, truth in advertising, there is a claim on the market that it's been detected, that it's there. It's not very statistically significant. If I were to bet, I think it would probably go away. It's a very hard thing to observe. But maybe as you get better and better data, cleaner and cleaner analysis, it will persist and we will have directly detected the dark energy.
So if we just take this tangent of dark energy, people will sometimes bring up dark energy and dark matter as an example of why physicists have lost their mind. We're just going to say that there's this field that permeates everything, it's unlike any other field, it's invisible, and it helps us work out some of the math. How do you respond to that? This kind of suggestion?
Well, two ways. One way is those people would have had to say the same thing when we discovered the planet Neptune.
Yeah.
Because it's exactly analogous, where we have a very good theory, in that case, Newtonian gravity in the solar system. We made predictions. The predictions were slightly off. The motion of the outer planets. You found that you could explain that motion by positing something very simple. One more planet in a very, very particular place. And you went and looked for it, and there it was, right? That was the first successful example of finding dark matter.
Matter that we can't see.
Neptune was dark.
Yeah.
There's a difference between dark matter and dark energy, right? Dark matter, as far as we are hypothesizing it, is a particle of some sort. It's just a particle that interacts with us very weakly. So we know how much of it there is. We know more or less where it is. We know some of its properties. We don't know specifically what it is. But it's not anything fundamentally mysterious. It's a particle. Dark energy is a different story. So dark energy is indeed uniformly spread throughout space and has this very weird property that it doesn't seem to evolve as far as we can tell. It's the same amount of energy in every cubic centimeter of space from moment to moment in time. That's why far and away the leading candidate for dark energy is Einstein's cosmological constant. The cosmological constant is strictly constant, 100% constant. The data say it had better be 98% constant or better, so 100% constant works, right? And it's also very robust. It's just there. It's not doing anything. It doesn't interact with any other particles. It makes perfect sense. Probably the dark energy is the cosmological constant. The dark matter, super important to emphasize here. It was hypothesized at first in the 70s and 80s, mostly to explain the rotation of galaxies. Today, the evidence for dark matter is both much better than it was in the 1980s and from different sources. It is mostly from observations of the cosmic background radiation or of large-scale structure. So we have multiple independent lines of evidence, also gravitational lensing and things like that, many, many pieces of evidence that say that dark matter is there. And also that say that the effects of dark matter are different than if we modified gravity. So that was my first answer to your question is dark matter, we have a lot of evidence for. But the other one is, of course, we would love it if it weren't dark matter. Our vested interest is 100% aligned with it being something more cool and interesting than dark matter, because dark matter is just a particle. That's the most boring thing in the world.
And it's non-uniformly distributed through space, dark matter?
Absolutely, yeah.
And so this,
you can even see maps of it that we've constructed from gravitational lensing.
so verifiable sort of clumps of dark matter in the galaxy that explain stuff.
Bigger than the galaxy, sadly. Like, we think that in the galaxy dark matter is lumpy, but it's weaker. Its effects are weaker. But on the scale of large-scale structure and clusters of galaxies and things like that, yes, we can show you where the dark matter is.
Could there be a super cool explanation for dark matter that would be interesting as opposed to just another particle that sits there in clumps?
The super cool explanation would be modifying gravity rather than inventing a new particle.
Oh.
Sadly, that doesn't really work. We've tried. I've tried. That's my third paper that was very successful. I tried to unify dark matter and dark energy together. That was my idea. That was my aspiration, not even an idea. I tried to do it. It failed even before we wrote the paper. I realized that my idea did not help. It could possibly explain away the dark energy, but it would not explain away the dark energy. And so I thought it was not that interesting, actually. And then two different collaborators of mine said, has anyone thought of this idea? Like, they thought of exactly the same idea completely independently of me. I said, well, if three different people found the same idea, maybe it is interesting. And so we wrote the paper. And yeah, it was very interesting. People were very interested.
Can you describe this paper a little bit? Like, it's fascinating how much of a thing there is, dark energy and dark matter, and you don't quite understand it. So what was your dive into exploring how to unify the two?
So here is what we know about dark matter and dark energy. They become important in regimes where gravity is very, very, very weak. That's kind of the opposite from what you would expect if you actually were modifying gravity. Like, there's a rule of thumb in quantum field theory, etc., that new effects show up when the effects are strong, right? We understand weak fields, we don't understand strong fields. But okay, maybe this is different, right? So what do I mean by when gravity is weak? The dark energy shows up late in the history of the universe. Early in the history of the universe, the dark energy is irrelevant. But remember, the density of dark energy stays constant. The density of matter and radiation go down. So at early times, the dark energy was completely irrelevant compared to matter and radiation. At late times, it becomes important. That's also when the universe is dilute and gravity is relatively weak. Now think about galaxies, okay? A galaxy is more dense in the middle, less dense on the outside, and there is a phenomenological fact about galaxies that in the interior of galaxies, you don't need dark matter. That's not so surprising because the density of stars and gas is very high there, and the dark matter is just subdominant. But there's generally a radius inside of which you don't need dark matter to fit the data, outside of which you do need dark matter to fit the data. So that's, again, when gravity is weak, right? So I asked myself, of course we know in field theory, new effects show up when fields are strong, not weak, but let's throw that out of the window. Can I write down a theory where gravity alters when it is weak? And we've already said what gravity is. What is gravity? It's the curvature of spacetime. So there are mathematical quantities that measure the curvature of spacetime. And generally, you would say, like, I have an understanding. Einstein's equation, which I explained to the readers in the book, relates the curvature of space-time to matter and energy. The more matter and energy, the more curvature. So I'm saying, what if you add a new term in there that says the less matter and energy, the more curvature? No reason to do that, except to fit the data, right? So I tried to unify the need for dark matter and the need for dark energy.
That would be really cool if that was the case. Like,
super cool, right? It'd be the best. It'd be great.
but it
didn't work.
But it'd be really interesting if gravity did something funky when there's not much of it. Like, almost like at the edges of it, it gets like, noisy.
That was exactly the hope. But the great thing about physics is there are equations, right? I mean, you can come up with the words and you can wave your hands, but then you got to write down the equations, and I did. And I figured out that it could help with the dark energy, the acceleration of the universe. It doesn't help with the dark matter.
It just sucks at the scale of galaxies, the scale of solar systems. The physics is kind of boring.
Yeah, it does. I agree. And again, that's why it is a little bit, I tear my hair out when people who are not physicists accuse physicists, like you say, of sort of losing the plot because they need dark matter and dark energy. I don't want dark matter and dark energy. I want something much cooler than that. I've tried. But you got to listen to the equations and to the data.
You mentioned 3 papers. Your first awesome paper ever,
Yeah.
and your second awesome paper ever. Of course, you wrote many papers, so you're being very harsh on the others. But,
Well, by the way, this is not awesomeness. This is impact.
Impact.
Right?
Sure.
There's no correlation between awesomeness and impact.
Right.
Some of my best papers fell without a stone.
Tree
and vice
falls in the
versa,
forest.
Right? Yeah. The first paper was called Limits on the Lorentz and Parity Violating Modification of Electromagnetism, or Electrodynamics. So we figured out how to violate Lorentz invariance, which is the symmetry underlying relativity. And the important thing is we figured out a way to do it that didn't violate anything else and was experimentally testable. So people love that. The second paper was called Quintessence and the Rest of the World. So quintessence is this dynamical dark energy field. The rest of the world is because I was talking about how the quintessence field would interact with other particles and fields and how to avoid the interactions you don't want. And the third paper was called Is Cosmic Speed Up Due to Gravitational Physics? Something like that. So you see the common theme. I'm taking, what we know, standard model of particle physics, general relativity, tweaking them in some way, and then trying to fit the data.
and trying to make it so it's experimentally validated.
Ideally, yes, that's right. That's the goal.
You wrote the book Something Deeply Hidden on the Mysteries of Quantum Mechanics, and a new book coming out soon, part of that Biggest Ideas in the Universe series we mentioned, called Quanta and Fields. So that's focusing on quantum mechanics. Big question first. Biggest ideas in the universe. What to you is most beautiful, or perhaps most mysterious about quantum mechanics?
Quantum mechanics is a harder one. I wrote a textbook on general relativity, and I started it by saying general relativity is the most beautiful physical theory ever invented. I will stand by that. It is less fundamental than quantum mechanics, but quantum mechanics is a little more mysterious. So it's a little bit kludgy right now. If you think about how we teach quantum mechanics to our students, the Copenhagen interpretation, it's a god-awful mess. No one's going to accuse that of being very beautiful. I'm a fan of many worlds interpretation of quantum mechanics, and that is very beautiful in the sense that fewer ingredients, just one equation, and it could cover everything in the world. It depends what you mean by beauty, but I think that the answer to your question is quantum mechanics can start with extraordinarily austere, tiny ingredients, and in principle lead to the world, right? That boggles my mind. It's much more comprehensive. General relativity is about gravity. That's great. Quantum mechanics is about everything, and seems to be up to the task. And so I don't know, is that beauty or not? But it's certainly impressive.
So both for the theory, the predictive power of the theory, and the fact that the theory describes tiny things creating everything we see around us.
It's a monist